So last time we got most of the way through how we do partial fraction expansion with discrete time systems, and it was similar to what you did with Laplace transforms for solving differential equations. Here we're using partial fractions that also could be used to solve difference equations, and with a little wind at our back, we'll see that. We're going to come full circle today back to how we solve the kind of problems that we could solve by solving difference equations, namely doing system analysis, finding zero state responses, zero input responses, including cases where we have initial conditions. And so just as transforms and partial fractions help us in continuous time to do that with differential equations, these partial fractions, or at least a version we have with Z transforms, will help us with discrete time systems and difference equations. So we got through the basic partial fraction expansions of how that works, and again, what was the kind of the big difference between when we do that in continuous time and when we do it now with discrete time? There was a upfront modification we had to make to the whole process. What was that? We've got to divide by Z, because all of our Z transform forms have Z's in the numerator. Our partial fractions, the expansion itself doesn't, and so we needed to now, if we're going to partial fraction expand the whatever it is we want to inverse transform, but not that function, but that function divided by Z, and then put the Z back when we get to the actually doing the inverse transforms. Okay, we handled simple poles last time and complex conjugate poles last time. The other special case we didn't get to was repeated roots, which have to be handled specially, just as they did in continuous time systems. And by repeated roots, I mean you have an h of s that you're trying to find h of n, and it's got a squared or a cubed term in the denominator with one of its factors, or that shows up in the y of z you're trying to inverse transform. And so when those do occur, if we have poles with powers more than just the first power, then when we do the partial fraction expansion, I need one partial fraction expansion term for each power of that pole function. And so if I have a squared function in the denominator, I need a term that goes with the square, and I also need a linear term. So we set up, the first key to doing this is setting up the partial fraction expansion, including all the right terms. And if I had a cubic here, I'd have a cubed term, a squared term, and a first order term. So we need one partial fraction for each of those powers of that pole term. And we keep going down until we get to a power of 1. And then we can stop there. Okay. No. Now, the coefficients of those we're going to need to find by a slightly different process. The coefficient of the term that goes with, well, whatever power we have, the highest power partial fraction term, in this case the A0 term, we're going to use normal partial fraction expansion process for that. So we'll multiply the function by that root to the highest power that it is, in this case z to the minus p2 squared, and replace z with p2, or yes, p2 in this case, with the value at that pole. And if you plugged it in and looked at the partial fraction expansion, did those operations on it, you would see that yes, all the other terms do cancel except the A0 term. So that's kind of making sense mathematically. Any other lower order powers, though, we're going to have to get those not by substituting their power in, because we'll still end up with some zeros where we don't want them. But what we do is take that original product of our function we're trying to inverse transform and the pole term at its highest power, that product, that thing we're getting the coefficient for before, and take its first derivative, or a derivative for each power we're trying to decrement to. And that's a derivative with respect to z. After we do the derivative, then we replace z with the pole value, in this case p1, and do a normal partial fraction determination on that. So if the root appears k times, this is the generic equation for all those derivatives we would need. If we have a root that appears k times, like if k would be a cubic if it was a third order system, then each of those partial fractions terms at the power that was k minus n would be found by a sub n is 1 over, that's n factorial, the nth derivative with respect to z of the same product, the h times the pole term raised to the highest power, and then that derivative evaluated at the pole term. Now, when might you get that? Well, if h of z has multiple poles, repeated poles and zeros, that's one case. Maybe a more common case is if h of z has a particular pole and your x sub z also has the same pole, and when you multiply them together to do convolution, then the product, the thing you're usually trying to inverse transform to find y, is going to end up multiple poles there. And that's a typical case where we might run into that. So we'll do that kind of case as an example. See if this is working now. There we go. So here's an h of z, a transfer function for a system. It's z squared over z squared minus 1. And I want to know what's the step response of that system. So I want to put in a unit step input and find what comes out. So and in this case, we'll assume we have a relaxed system. So we'll do convolution using transform multiplication, which means I need x sub z, the z transform of the input signal, which is z over z minus 1. We're going to multiply that by h of z. So now we have this product. And if we combine terms, our x of z times h of z, which is the output z transform, is going to be a z cubed over z plus 1 times z minus 1 quantity squared. Now I've got that repeated root. We take away 1 power of z from the numerator and tuck that away for later. So we just have z squared in the numerator. And now I have a proper rational fraction. And we'll expand that out into partial fractions. We have the first single pole term, and the double pole term will give its own coefficient at the z minus 1 squared, and a second one at z minus 1. Okay, yeah. Previous slide. Missing some information. Okay. Is that slide like really blank? Ah, it's really blank. Okay. Sorry about that. Basically, h of z may have multiple poles, or the product x of z and h of z may have multiple poles. And the example we're doing is like that second case. X of z had a pole at the same position that h of z had a pole. And so when we make the product to find y of z, it has a repeated pole. I just blew through the process. That's pretty much the way we've been doing transform convolution before. If there's any part of that that people aren't comfortable with, let's talk it through. That's important stuff. That's what we came here. That's what we paid all this money for. Come learn about it. So we don't have to do convolution. We're doing it effectively in Z transform land by multiplying things. All right. Okay now? So here's our partial fraction challenge. We've got 3 terms. The first one is just plain old partial fractions. We take the z plus 1, multiply it by our y prime of z. That cancels one of the terms from the denominator. We replace z with minus 1. And then it's just algebra. Turns out to be a quarter. And even that second, the a0 term, we're going to multiply the y prime of z by that whole denominator, including the square of it, which gets rid of the whole square term in the denominator. Evaluate it at z equals plus 1, and then we get 1/2 of that. Now we need the derivative to get the next level down. To get the linear one, we take the derivative of not y prime of z, but y prime of z times the z minus 1 squared term. And then that's what we take the derivative of. In this case, that's z squared over z plus 1. And whether you're better with the multiplicative or the different derivative, multiplicative or division rule for derivatives, you can derive what that derivative is going to be and just combine those terms together. Replace again, z is still plus 1. It's still the value of z at that pole position. And so plugging that in, we get 3/4. All right. So we got these answers, 1/4, 1/2, and 3/4 for our coefficients from the partial fraction expansion. If we look those up in the table, we put the z back in for y of z, so each of our terms now has a z back in it. And the first term is look for z minus, so it's z minus minus 1, which is a minus 1 to the n u of n with the coefficient out in front. The square term in that table, that's what gives us the n times. And the first order term gives us just a unit step. Okay. So that's the last kind of special case we have to deal with partial fractions with discrete systems. So simple poles, complex conjugate poles, and repeated poles. And we would, again, if you had a cubic or a even higher order one, we would just keep doing derivatives of that product of y prime of z and the pole term at its highest order. Okay, and I think there's a practice problem to try out there on homework. Questions? Yeah.
Different ways of doing this. Is it like if we're more comfortable using the other way?
There are other ways of doing it algebraically, and if they work for you, go for it. Yes, you can set up equivalent fractions and match numerator terms and all that kind of stuff. There's 3 or 4 different techniques. Yeah.
All right. Sorry, you have to repeat yourself. You said, 2 days ago that there was something especially you could do with these that you couldn't do with the continuous time. What was that?
There was something we can do with these.
Something you can do in the domain that you couldn't do in continuous time.
Well, there's certainly certain kinds of filters we can make with discrete time.
I'm saying, like, in terms of, I think...
In terms of partial fractions?
Yeah, either partial fractions or just finding, like, the transfer function or the, I guess, I remember you saying there was something, and I was really interested in what it was, but I forgot. Yeah, I think that's what it was.
Okay. Yeah, well, I mean, and that's a little bit of a contrivance, just because we're trying to make the terms look like the ones in the transform table.
Oh, yeah.
Right. And we don't have to do that because the Laplace transforms generally don't have s's in their numerators. If they did, we'd probably play the same game. Was there a question? No? Okay. All right. Some exceptions. This only works if you have strictly proper rational functions that you're trying to inverse transform. And so if you don't, what do? Well, the h of z, or the thing you're trying to transform, doesn't have to be. It's the thing that you have to pull the z away. And just like in continuous times, if you don't meet the requirements, a little polynomial division will get you out of it. So we do long division, literally divide the numerator by the denominator. In this case, if we did that, we'd get a 1 with a remainder of z minus 1. So we would rewrite our divided version as some whole number term and take the remainder and put it over the denominator. And then we would do partial fractions, not on the whole thing, but just on the remaining part. So leave the constant. Partial fraction expand the remaining ratio that we have for h of z or y of z, and just use verbal partial fractions after that. Yeah. Can you go back one? Tell me your thing doesn't have the polynomial division on it. It doesn't. Oh, sorry about that. Old slides. What's that? Yeah, that's right. Probably good to write down once, just to refresh your memory on how to do polynomial long division. want to get to so much more. So I get to. Okay. But the important thing is the process. So we force it to be strictly proper. Now I've got I'm okay there. What's that constant going to inverse transform as? A delta function, right? And in fact, if we go through the partial fractions, well, actually, once we put it back in, put the z's back in, it comes across, we have a z that we have to inverse transform, but that's just a shifted delta function. In this case, it's delta plus 1. So, gee, that said, I got a non-causal impulse response. Well, it came from the fact I started with an h of z, back up to that guy, that had a z cubed in the numerator and a z squared denominator. So I had more zeros than I had poles. So, okay, that follows that rule we had, that if you want a causal system, you got to have at least as many poles as you have zeros. So I guess this is all kind of consistent. Okay, now what are we going to do with this stuff? Well, we know we just did this, when we know now we can do this. We can do zero state responses, we can do convolution with z transforms, as long as now with partial fractions we can do any inverse transformation that we need to do. But is there anything else we can do? Well, I keep promising you this, now the time has finally come, that we can do something we can't do with Fourier transforms, and that's finding the complete system response, including initial conditions. If I put in a causal signal to a system that has some initial conditions and has a causal unit sample response, what's the system going to do? And so for that, it requires not our standard form of the Z transform, which is actually called a two-sided Z transform, but it needs a one-sided or causal Z transform, which is identical except the lower limit of the summation is not minus infinity, it's changed to 0. So I'm only summing from n equals 0 forward to positive values of n. And so it's only good for causal systems, because I want a causal h of n. I don't want any information for negative values of n, or I'm missing them. If we're inputting causal signals, same thing. If I'm going to use their transform, I don't want to be throwing away information, so it's only good for causal inputs. But it can be used for non-relaxed systems. And it can be used for non-relaxed systems, or at least it can help me solve non-relaxed system problems, because it has one property that changes on us. Most of the properties, scaling, times n, convolution, those are all the same for both the one-sided and the two-sided Z transform. And that's good news that the convolution property is the same, because we need that. The one that's different is the shift property. And again, this all parallels what happened in Laplace transforms, between one-sided and two-sided Laplace transforms. If you have a signal that itself is not fully causal by itself, and you're working with its Z transform, so you've knocked off some information, and then you try to shift that signal, you've got to be careful. The shift property for the two-sided Z transform is take a signal, shift it, you get just z to the minus 1 times the transform, right? Z to the minus 1 was our shift operator. And if I shifted by 2, if I delayed by 2, that'd be z to the minus 2. Or if I advanced by 1, that would be z to the plus 1. That was the two-sided transform. So it looks like this. If here's some y of n, right? And we take the z transform of that whole thing, that gives me a nice y of z. Then if I take that y of n and shift it over by 1, then the transform of that is z to the minus 1 times y of z. So that's, and we're supposing you've done the summation over the whole, all values of n, so the fact that it's shifted doesn't really affect anything. Not so if I take that same signal that's non-causal by itself, and find its one-sided Z transform. So let me do that. We'll take y of z is just the sum beginning at n equals 0. So I've ignored all this other data when I take my transform. So my transform doesn't include that information. Now if I shift that over, if I delay y, and look at what I've got, well, I can account for these samples, when I take the z to the minus 1 times the one-sided z transform that I came up with up there. But I'm missing this. This suddenly got shifted in. And so the change, the new thing for the one-sided z transform shift property is if I delay, if I shift by 1, I need to add a y of minus 1 term. I need to know what that previous piece of information was for the shift. And that's what's going to let me play with initial conditions. In Laplace, it was the derivative property that changed. Here in Z transforms, it's the time shift property that changes. Now, that's kind of the connection between the two, right? We had derivatives and differential equations in Laplace. We have difference equations in continuous time. So those are kind of the analogous operations between those two domains. And so that's why this is showing up here. Okay? So if you have a signal that's non-causal, and you've found its one-sided Z transform, if you then shift it, you need to add this initial condition term to the shifted Z transform, and the process just repeats. So if I shift by 2, I've got to apply the property twice. So y of n minus 2 is the z to the minus 1 times that whole thing plus another initial condition. Yes, Natalie?
So, are we assuming that, I guess, a lot of the signals we work with are causal.
We generally don't, but when I have an initial condition built into my system, then my system, although its response is non-causal, I have what the system would consider a non-causal input. I had some previous inputs I'm still working on, and so I need a way to account for those, and that's where it's going to help us.
So if there's a causal system that has these conditions,
that's when we use this, right? And if we have a causal system with no initial conditions, I just don't even bother. If I have a relaxed system. So even if we were applying this property, as soon as you tell me I have a relaxed system, those initial condition terms go away, at least in terms of h of n and the system response. Okay. And it's this extra term that's going to give us the terms we need to do system analysis now with initial conditions. So here's the method, and we'll take an example through this method. Actually, let's just do it as we go here. No, let's do a method because we're going to want to see how it works. You're going to transform the difference equation just like we normally do, except this time when we do apply the shift property to transform the equation, we're going to end up with some extra terms, the initial condition terms, on the y side and the x side. So we're going to use that right shift property when we do that. Then we're just going to rearrange the terms just like we did before, but now they're going to include those initial condition pieces. We'll substitute in the real x of z and the real initial conditions, and then take that mess and partial fraction expand back to the time domain. Now that doesn't seem like that's much different, so let's take this example. Let's take our simple recursive filter, 1/2 Vn u of n unit sample response. There's the difference equation. We've already got the transfer function. We already know the frequency response. We're good to go. And we want to find the step input, which we've done before. But now I want to do it with an initial condition. Y of minus 1 is 10 will be our initial condition. When we've done this before, we didn't have an initial condition. Alrighty then. So let's go to work. Y of n is, that's y of n. Let's rewrite the, let's keep it that way. Minus 1/2 y of n minus 1 equals x of n. That's our difference equation. Okay. Now that I've got that, let me put the process back up there so we can follow along with it. Find the one-sided z transform of the difference equation, term by term. So we'll one-sided z transform of that. Y of n becomes y of z minus 1/2 y of n minus 1. Let's see, that's a z to the minus 1 y of z. Get my signs right, get my signs right, get my signs right, plus little y of minus 1. Double check. According to that property, right? And equals x of z in this case. Now, if we'd done that before, let's do our relaxed case. Oh, that's not going to work. Let's do it over here. If we were just doing zero state responses, right, we would have said y of z is y of z times, I'll do it the same way, y of z minus 1/2 z to the minus 1 y of z equals x of z. So almost the same thing, except we've got this extra term now. Okay, what does it say now? Use the right side shift property to include initial conditions in any delayed terms. We did that. Don't need it over there. Rearrange to get y of z as some function of stuff. Y of z times 1 minus 1/2 z to the minus 1 plus y of minus 1 equals x of z. Again, this is little y. This is a time sample. This is big Y. This is a z transform. I'm sorry? In front of the y of minus 1. Oh, there should certainly be a minus 1/2 in front of that. Thank you. Yeah.
Why was the y of z plus y minus 1 almost put by 1/2? Why is that bracketed together?
Why is this? Because I'm replacing y of n minus 1 with this whole term. According to the shift property, the delay gave me this plus the initial condition term. Okay? So now I have y of z times this. I think I'm going to have to put y of z. Hang on to that. I'm going to have to bring this over here. X of z plus 1/2 y of minus 1. And then this is multiplied by this, so I think I'll have to divide everything by that. And get the output transform in terms of x of z and the initial condition. So far, so good. Whereas if we had done that same thing over here in our relaxed system, we would have keep picking up a dead marker. We would have ended up with over minus 1/2 to the minus 1. Right? Okay, next step, substitute in x of z. Uh-oh, well, what is x of z? X of n was a unit step. Remember your transforms. What's x of z? z over z minus 1, or if you like, it's 1 over 1 minus z to the minus 1, either one. Okay. So we're going to substitute that in here. Let's go up here. As z over z minus 1 for x of z plus 1/2 y of y of minus 1 and over 1 minus 1/2 z to the minus 1. Now I know what y of minus 1 is too, right? That was our initial condition. Yes, it's 10. And what else can we do here? This is getting a little messy. I've got positive and negative powers of z. So let me multiply by z over z because I want to get rid of that negative power of z thing there. And we're going to want to combine terms on our input here. So let's hang on to the z out in front for a moment. I'm going to have z here plus 1/2 times 10 times the quantity z minus 1 all over z minus 1/2. I hope, if my algebra is holding up. It was in the denominator of this term, so I'm going to multiply it through by both to get rid of that. Everybody okay with all the operations so far? Yeah. So yes, so we did that. I think I'm okay. Okay, what am I going to call it here? Let's see. So what do I have? What do I have? What do I have? I have too many z's is what I've got. No, I don't. I'm all right. So I think I've got a z squared in the numerator. I've got 1/2 times 10, that gives me a 5. That's 5z minus 5, I hope. 5z squared minus 5z and a z minus 1/2 in the denominator. Yeah. So I multiplied my numerator by 1.
Yeah. You multiply, so you minus 1 that you're canceling out on that first, that works, but then you still have the minus 1 with the denominator that you're multiplying by, so it just goes right back in. So I would need to keep that in and multiply the denominator by the minus 1.
You want me to use this? I agree. It always gets messy when you go off your notes and do it different than how you did it. Thank you. You got to keep, oops, so I'm going to need that here. Z minus 1, thank you. I combine some terms. 6z squared minus 5z over that product. And we'll factor out a z, I think. Z minus 5 minus a half. Whew. So that's my y of z. Okay. Now, we can partial fraction expand. So let's tuck away our z. That's going to be a 6z minus 5 over z minus 1 times z minus a half. And we'll break that into partial fractions. I'll call it a over z minus 1 and b over z minus a half. That's a z. Simple poles, no repeated roots. If you go through the partial fractions, what we'll find out is, what is our a? Our a turns out to be 2. B turns out to be 4, it looks like. So we'll put back our y of z is a 2z over z minus 1 and a 4z over z minus a half, which we can inverse transform. Let me go up higher because we're getting low there, so we'll come over here. So our output y of n, inverse transform of that, z over z minus 1 is a unit step with a 2 out in front. Z over z minus a half is a 1/2 to the n u of n. And I've got a 4 out in front. And that's the step response. There's the forced response. Put in a unit step, I got something like a unit step out. This must be the natural response. And we would call this in our old lingo a total response. It has the forced and the natural response, and it has the zero state and the zero input response. The zero state response came from this part. The zero input response came from that part, the initial conditions. Okay. Questions about the process? Well, let's do it this way. Let's do it back in the relaxed, finding just the zero state response. See how that's different. Here we would have had the same x of z, so that was z over z minus 1. So our y of z over x of z would be z over z minus 1 times 1 minus 1/2 z to the minus 1. And let's do a z over z again to bring this up to a higher power of z. Z squared over z minus 1 and z minus a half. Which would look an awful lot like what we had going on over here for our zero state response. And if you partial fraction that, well, let's do it the same way. which you would have gotten, this was a 2, and B is a -1. Oops, and actually, when we partial fraction expanded, we would have taken that away, right? So our zero state response, inverse transforming that, would have been 2u of n, and it's a 1/2 to the n u of n, which the force response piece should match up, because that comes from the zero state response. Here we got a different answer for the natural response piece, because here's the total natural response. This is the part of the natural response that came from just the input, which means the rest of it came from the zero input response, right? No, this actually came because this came from the same part as over there, the x of z times h of z part. This, where I have the initial condition, that's what generated the part of this response that was the zero input response. In fact, we can go find it. Shall we see what the zero input response was? Everybody's okay with what we got so far?
Wait, can you show the circle one more time?
I'll leave it up there. It's but let's see how to find a zero input response with this method. Okay. So we still need that transformed difference equation using our initial conditions, which we have here. Y of z minus a half y of z minus 1, oops, quantity there, plus our initial condition. Right? Except for a zero input response, what is my x of z? 0. So this is the equation we're going to be solving for the zero input response. And so similarly, we do the same kind of thing. We get y of z times 1 minus 1/2 z to the minus 1 is now, well, there's nothing over here for x of z. The only thing left is the minus 1/2 y to the minus 1, which comes over to the other side. Which we happen to know that was 10. So that 1/2 of that's going to be 5. So y of z is just 5 over 1 minus 1/2 z to the minus 1, which is the same as 5 z over z minus a half. Which we can directly inverse transform. That's 5 times 1/2 to the n u of n. That's our y0 input response. So I should be able to add this to this and get that. Well, we saw this came across. I have plus 5 of these 1/2 guys, minus 1, better give me 4. It worked. Okay? So this structure, the context, the basic ideas are all the same as they were when we were doing this solving difference equations. We're just using Z transforms to solve the difference equations, using multiplication to handle the convolution piece for the zero state response, using linearity along the way, and this shift property for the one-sided Z transform to get us the initial conditions.
Is there a way for us to practice this? Is this something you did homework 6 at all, like the last one?
I'll make sure it is.
Okay.
Yeah, there'll be a practice problem on it.
There will be?
Yeah. All right, questions?
Homework 6 you did?
We're not turning in homework 6, just for practice.
Oh, yeah.
See you on Friday.
Oh, yeah.